So today we're just going to go over some glycolysis. Whoops, notability. And so before we dive into specific practice problems, we need to look at the whole stage of where we're at. Glycolysis is just one pathway whereby we convert glucose where we have glucose, and as a result, we get ATP. We also get NADH. We ultimately convert that to pyruvate. Wherever we're at in uh, the metabolism pathway, the energy molecules that we will produce will be NADH, FADH2, and ATP. ATP we can use right away for energy, muscle contraction, sodium ion channels, NADH and FADH2 come later. These will go into the electron transport chain, which we will talk about likely tomorrow or Monday. Electron transport chain. And from there, that's where we actually generate the bulk of our ATP. And here's something to keep in mind. You do have to keep straight which one's the oxidized form and which one's the reduced form. So let's go back to Chem 352. Oh wait, we're still there. Remember a long time ago where we took a carbonyl and we reduced it with sodium borohydride to get an alcohol. What's the actual reducing agent in here? It's hydride. So NADH and FADH2 both contain the equivalent of a hydride ion. H minus, and this is really H minus and H plus because it's the same thing, but it goes through a slightly different mechanism. Um, and you remember that hydride is what did the reducing. So always know that your reagent with the hydride is the reducing agent. And then the counterpart, NAD plus and FAD, no plus, that will be your oxidizing reagent. Yeah. Okay. So with that in mind, let's do a little bit of just general bird's eye view of glycolysis. So this is on Learning Suite. Take a second to label all these molecules and figure out what goes into the blank spaces. Do that for 3 minutes. All right, you want to work on it or need more time? Okay. So the first half is where we have the investment phase, where we activate glucose and then split it into two pieces. So the first thing is we just have glucose, which is phosphorylated with what? ATP, yes, which makes glucose 6 phosphate. And then it does an isomerization to make what? Mm-hmm. And then that gets split into two molecules, which are glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. So during the first four steps of glycolysis, two phosphate groups are transferred to glucose via phosphorylation. And I'll just say this right now. So I have a table later on down here that lists the enzyme, the reactants, and the products, and the reaction type. None of this is really new chemistry. It's just applied in a different context. So phosphorylation is really, come on, zoom in. Phosphorylation really is the organic equivalent of nucleophilic acyl substitution. So remember way back when we had a carbonyl, we had a nucleophile and we generated a tetrahedral intermediate. And depending on if we had a good leaving group on it, we could reform that carbonyl. Now, this is the same idea, but now we have the phosphate, which has 5 individual bonds on it. Oh, one of the oxygens has a good leaving group on it. When a new nucleophile comes in, which in this case it's always going to be an alcohol OH group, is actually going to form a, whoops, that's a minus. Oh, I drew too many oxygens. Nucleophile, O, leaving group, and then that comes down, and then that kicks off. So this right here is the pentavalent intermediate. Pentavalent meaning 5 bonds. He has done this before, where it's like this carbon is carbon 13. Which one of the mechanisms shows the correct mechanism? He likes to, in our seminar class, he liked to drill his graduate student on the tetrahedral intermediate. So I would definitely expect to see something like that on your next exam. Do not never ever go from here to here. That's wrong. It always breaks the carbon oxygen pi bond. That carbon oxygen pi bond comes back down, breaks another bond. So, okay, that's phosphorylation for you. Again, not new chemistry, just looks a little bit different. Okay. Where ATP is converted to ADP. The end product is what? Yep, 1 fructose 1,6 bisphosphate. All right. And here's the interesting step. So this is where fructose 1,6 bisphosphate gets split into two fragments. Dihydroxyacetone phosphate, or DHAP, and glyceraldehyde 3-phosphate, or 3P, G3P for short. And this is important. It's the acetone that gets converted into the glyceraldehyde. And that one right there, let's see, that's the third step. Did this one, and did this one. This rearrangement right here really just has to do with enol and keto tautomerization. And that's the same for converting the glucose 6-phosphate into a fructose 6-phosphate. It's just opening up the chain and transferring between the enol and the keto form. And that we've all known and seen before, which again, it's not new chemistry. It's just with a bunch of other random stuff involved. All right, now the second part, oxidation and formation of ATP. All right, take a couple minutes, work on that, and then we'll work on it together. All right, let's work on this together. So let's keep in mind that not all ATP formation steps are irreversible. In the in the investment phase, this is irreversible. This is, oops, I forgot to add the ATP there. This is irreversible. Ooh, irreversible. It's not good handwriting. Um, and the final one is irreversible as well. Why is that? So we're going in each of these steps, which are 1, 3, and 10. We are we are going from a phosphoanhydride. That's much better. Is my handwriting still better than Dr. Price's, or it's I don't know. Phosphoanhydride, which was one of our most reactive electrophiles in our nucleophilic acyl substitution chapter. And we're transforming that into a phosphoester, which is level 2. So obviously that's going downhill energy, releasing energy, not reversible. Now, when we look at this step, when we are, what is it? When we're taking when we're converting 1,3-bisphosphoglycerate to just the 1-bisphosphoglycerate, those are both the same level 2 electrophiles. So in this step, I don't remember which step it is. This is the only one that is reversible because because the reactant and the product have similar energy levels. It's not actually it's close to zero, not actually zero, but it's low enough that it's easy to go back and forth between the two. And it's in this step right here that we regain the 2 ATP that we use uh, to start the glycolysis process. So let's see. So both molecules of glyceraldehyde 3-phosphate become oxidized using, yep, because that's our oxidizing agent. NADH will come back to haunt you in the electron transport chain. NADH. NAD plus, which simply becomes NADH. This process releases energy, talking about this step right here, which is used to attach the phosphates to the sugars, making them 1,3-bisphosphoglycerate. And now here, in the final step of the process, this is where we actually get our net gain of 2 ATPs molecules. So during the last 4 steps of glycolysis, the phosphate groups of the molecule in a phosphoenol pyruvate, which is converted to pyruvate. Let's see, transferred to ADP, creating, what does it create? ATP. This is done via the process of substrate level phosphorylation. And then this last molecule is 1,3-bisphosphoglycerate. Now, as with all organic reactions, all right, let me say this. What's the number one rule of retrosynthesis I told you about? Count your carbons, yes. So is the total number of carbon atoms conserved? Yes. Well, yes, always, because the conservation of mass always applies. But I want you to notice that unlike the terpene chemistry, where we generated a carbocation, which was susceptible to rearrangement and cascade cyclization and all that, here we have no rearrangement whatsoever. All of the carbons will maintain their same relative order regardless of what molecule they're in. So I have here from a Journal of Chemistry Education, who knew you could publish in academia in an educational journal. But just as we did before, we want to label our individual carbons to keep track of where everything's going. So 1, 2, 3, 4, 5, 6. So the first few steps, it's pretty easy because we're just shifting around this end of the molecule. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And now here's the part where it gets a little tricky. Because here's where whoops. Yeah, I lost my thing. Because this is where it gets split into the two different three carbon subunits, dihydroxyacetone and glyceraldehyde 3-phosphate. Let's see. So the left side, wish they drew it in the other way, but it is what it is. What did I want to do here? No. 3, 6. So this left side gets converted into glyceraldehyde 3-phosphate, and the right side gets converted into dihydroxyacetone phosphate. So based on the position of the phosphate groups, it's really easy to tell which is carbon 1, 2, 3, and 4, 5, 6. So here, in dihydroxyacetone, carbon 1 had the phosphate, and then obviously it's just 1, 2, 3. Then over here, it was 6 had the phosphate, and it's 5, 4. I would imagine there being an exam question about this. Okay. And now you can just follow the same logic. So that gets converted into dihydroxyacetone phosphate. So going forward, the labeling will always be 1, 6, because see the phosphates stay in the same group. So it'll be 1, 6, 2, 5, and 3, 4, all the rest of the way down. And I'll just label that for consistency. 2, 5, 3, 4, 1, 6, 2, 5, 3, 4. Lactate is something else. 1, 6, 2, 5, 3, 4. So that's how I keep track of the individual carbon units. And with that, we're going to practice that. So where did the labeled atoms of glucose end up? Where did the labeled atoms end up with glucose when glucose is catabolized to each compound? So I'll get you started. So let's label our carbons. 1, 2, 3, 4, 5, 6. This molecule right here is 2-phosphoglycerate. This is lactate, which is the reduced form of pyruvate. And this is acetyl CoA. Okay, take a second to work on that for a little bit. All right, ready to work on it? Yeah. All right, okay. I'm going to draw two separate molecules of 2-phosphoglycerate, for which you'll understand in a second. Okay. So let's review. So I labeled it 1, 2, 3, 4, 5, and 6. Let's figure out where those carbons are in 2-phosphoglycerate. That is, where did I put that? 2, 6, 3, 4. Hold on a second. Let me make sure I'm doing this correctly. Good morning. This is 1, 2, 3, and this is 6, 5, and 4. Okay. So you notice that the blue carbon is which carbon? Number 1, yeah. So the blue one will end up right here. And then the other one was on carbon 5, and that was in red, highlighted red. It's going to end up right there. So notice that they're in two different molecules. That's because we split the fructose 1,6 bisphosphate in the 6 carbon unit into the 2 3 carbon units. And so it's exactly the same with pyruvate, where it's 1, 2, 3, and 6, 5, 4. Oops. I want to copy that first before I do anything with it. Yeah, copy. That's rather large. Okay. 1, 2, 3, 4, 5, 6. So let's see, the blue one is on carbon 1. So where's it going to show up in lactate? Mm-hmm. Yeah. You have a question?
Wait, can you, how did you number that?
So this is something I went over a little bit earlier. So I numbered it like this. Just 1 through 6 in the original cyclic glucose or cyclic glucose or fructose forms. And then when we split that up, the orders reverse. So the right side, whoops, split it up into 2 here. So the right side gets converted into glyceraldehyde 3-phosphate, and the left side gets converted into dihydroxyacetone. Wait, no, right goes with dihydroxyacetone, left goes with glyceraldehyde 3-phosphate. And using the phosphate groups as the handles, you can figure out which carbon is which. So here, this is carbon 1 here that had the phosphate group. So this is where carbon 1 will be here as well. And carbon 6 had the phosphate group here. So it'll be 6 here and then 654. So and then when you continue on with the pathway, 1 corresponds to 6, 2 goes to 5, and 3 goes to 4. Because these molecules, there's no rearrangement of the carbon chain.
So that's what, okay. So if you scroll back down.
Yeah.
So when you numbered it 1, 2, 3, and then you went 6, 5, 4, you were saying that's how they match up.
Yes.
Okay, I was just confused because I was like, there are not 6 carbons.
Yes, there are two different there are 3-carbon subunits. That's what trips people up a lot because you have 2 separate molecules. Okay, carbon 5 was here. Where's it going to show up in the other molecule of pyruvate? Yep. So this is why I drew it twice. They will show up in 2 different molecules that are the same. Well, they're not actually the same. They're the same molecule. They're 2 different molecules of the same chemical. Now, this one, acetyl-CoA, is a little tricky because this acetyl-CoA comes directly from pyruvate. Here's pyruvate. What's going to happen there is you're going to end up losing carbon dioxide. So pyruvate, the labeling was the same. So I just did it right here with lactate. So it's 1, 2, 3, 4, 5, 6. So I'll just draw this out this time because it's an easy molecule. Where does carbon, let's see, it's carbon 1? Yeah. Where does carbon 1 show up? In acetyl-CoA. Yeah, it's just this one, right? Whoops. It's just this one right here. Now, where's carbon 5? Oh, right. Wait, in the last section, I said it just came off. Oops, I'm going to have to correct that. But yes, it does just come in. Where's my highlighter? Yep, and there's my carbonyl. And of course, you also have carbon dioxide floating around in space. All right.
3 and 4 that are lost to CO2 formation.
Yes. Any questions about that? All right. This is the last practice problem I have planned for today, and then we'll call it good. So mannose is a monosaccharide obtained in the diet from fruits such as cranberries and currants. Catabolism of mannose occurs by conversion of mannose 6-phosphate to fructose 6-phosphate, an intermediate in glycolysis. Draw a stepwise mechanism for this process. So the first thing you're gonna want to do is convert it to the open chain form. So let's start with that. So and then I'll let you do the rest. Let's label the carbons. So this is an OH sticking out. This is a base from the enzyme. It'll pull off the proton right there. Whoops. Oh, that's my pastel thing. So that pulls off the hydrogen. This hydrogen comes down to form the aldehyde. This bond breaks and picks up a proton from an acid. And that gets us to I'm just going to abbreviate the phosphate group as P. Then from there, convert this into fructose 6 or fructose 6 phosphate. I don't really like learning about glycolysis that much, and you probably don't either. But if you're taking the MCAT, you'll do 41 in the fall.
Other if you use like an acid catalyzed enzyme or a base one.
Depends. You can show me after we're done. As long as it makes sense, it should be fine.
This album is 654 dihydroxyacetone phosphate.
Yes. All right. I'll work on this problem. All right. So the thing you want to notice is, well, obviously what changes is the size of the ring. But what's happened is that the hemiacetal, instead of being between the oxygen and carbon, instead of hemiacetal. So the hemiacetal was at carbon 1, but now over here it's in carbon 2. So where does the hemiacetal come from? It comes from a carbonyl. So what you need to do here is convert this, whoops, you need to switch the two groups. This, the carbonyl, needs to become the alcohol, and this alcohol needs to become the carbonyl. There are a couple ways to do this, but I'm going to do it like this because this is just what makes sense to me. So here we just take a base, which comes from the enzyme. It's going to deprotonate that alcohol. That'll bring these. Now, let me do my reactions and action arrows in a different color. I don't know if anyone actually looks at my notes. Okay, so it goes down there, forms the carbonyl. Wait a second. No, we have to do the tautomerization first. That's what makes these problems tricky. So we have to tautomerize right there first. Get to that ene diol. And how would we do that? So I'll just use this hydrogen because that's an alpha hydrogen. So we have a base, which comes from the enzyme, deprotonates that. This comes down and forms, whoops, that's not a good arrow. That goes down here and forms the bond right there. And then this arrow, then the pi electrons from the carbon oxygen pi bond come off and pick off a proton from some acid. So that's how we get the ene diol. And after that, then we're in a position to oops, I didn't mean to erase the ene diol part. I just need to get the bonds here. So once we get the ene diol, we're in a position to switch the carbonyl. So now we can take our base from some enzyme. This is actually very difficult to do in the laboratory, by the way, because the base could indiscriminately deprotonate any of those other protons. So the base comes and pulls off that proton. This comes down and forms the carbonyl. This comes up and hops onto the oxygen. And then, and let me redraw it out very quickly. P got OH on the end. Carbonyl there. Da, 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 da. H. 1, 2, 3, 4, 5, 6. Then we do a ring closure here. Let me draw out this again. So we'll have a base from the enzyme. Pull off this proton. That'll attack this carbonyl. And then those pi bonds will come up to pull off proton from an enzyme, acid. And we get our final product, fructose 6-phosphate. If you ever need to switch where the carbonyl is, remember you have to go through that ene diol intermediate. That's what allows you to what is it? It's a tautomerization. Is this a tautomerization happening twice? Which is what was I saying earlier? All of these are written as one step, but especially when you're doing the tautomerization, it's actually happening through multiple steps. It's one transformation, but a lot of arrow pushing to get where we want to be. All right. That is it for recitation today. Let me stop the recording.